actually looked at two major equations after looking at the basic structure of the DC machine. We looked at lap winding, wave winding, and we said why one would have the number of parallel paths as many as the number of poles, and the other one will have only two parallel paths. We talked about that, and then we wrote the equation for EMF, right, generated is going to be equal to whatever is the back EMF constant. I may call this as KE multiplied by omega multiplied by phi, where KE is equal to, we'll have the number of poles, number of conductors divided by 2 pi A, right? So let me write this again, where P equal to number of poles, Z equal to number of conductors, and A equal to number of parallel paths, right? This is what we wrote, and omega is the speed in radians per second, and phi is the flux per pole in Webers, of course, right? We also said the torque equation. So torque or the electromagnetic torque is equal to whatever is the same KE, back EMF constant holds good in this case also, multiplied by, I'm going to multiply this by phi and IA. Again, phi is the flux per pole and IA is the armature current, right? This is what we wrote as the EMF equation and the torque equation. Now, based on this, we started discussing, first of all, what is the open circuit characteristics of the machine. So we were talking about OCC or open circuit characteristics. This is valid when I am talking about the field excitation that can be changed. That means I am looking at the field system having only an electromagnet, not a permanent magnet. Not a permanent magnet. I am going to inject a field current, and according to the field current that I am injecting, I am going to get different values of flux, because the MMF is changing, the flux will also change. So if I draw, actually I can draw basically IF on the x-axis and flux on the y-axis, first of all. And if already the machine has been operated several times with a particular direction of the field current, then there may be some amount of flux left over as residual flux. So I may have some residual flux, maybe to the tune of, 1/10 or 1/15 or even less than that, as the quantity that is left over as compared to rated flux. So I am going to have this residual flux, and as I increase the field current, I am going to see that the flux is increasing, and then it reaches a particular value and almost saturates there. That's it. There is hardly any variation of flux beyond this particular value. So let us say this I call as IF rated, which will also imply that I have a particular value as phi rated, and this is going to be residual flux. This is going to be the residual flux value. So how will we define this IF rated? If we try to actually look at it, generally we tend to operate very close to saturation. Before it reaches completely the saturation point, we are going to operate it at a point which is known as the knee point of operation. So if I actually look at the characteristics as, corresponding to my leg, where it is going to bend near the knee region, so that particular point we call that as the knee point of operation. So this is actually knee point of operation. Okay, so this is the knee point. That's where normally we operate the DC machine. So rather than now drawing the flux versus field current, if I try to completely draw what is EG versus field current, right? What is the generated voltage versus field current? I am probably going to get some value of generated voltage even when the field current is 0, because there is some residual flux as long as I have rotation in the armature. So I'm going to rotate it probably at rated speed. If a machine is given, generally it will be given the nameplate details with what is the maximum current it can withstand or the average current that you can pass through the machine, how much is the voltage you can apply to the machine if it is operating as a motor. It will also tell you what is the rated speed, what is the rated power. All those things will be given. So in which case I should be able to say clearly whether I am operating it at rated speed or not. So the prime mover is going to rotate it at probably a particular speed. So let me say maybe omega equal to rated speed. Right? I am operating this at rated speed. So if it is a 220 volts machine or something like that, maybe when I am applying the rated value of field current which is corresponding to rated flux, I will get 220 volts as the value of voltage. So this is going to be rated voltage. So I'm talking about 220 volts as the rated voltage in this particular case. So when I am running the machine at rated speed with rated field current being applied, I will get the voltage which is supposed to be the rated voltage of the machine. Right? So I can specify this as though if I am measuring it across the armature, please note that the DC machine will always be specified with the circle which is representing the armature with 2 brushes on either side. This is the representation of the armature of a DC machine. Always. You will never ever show a brush for AC machines. Only for a DC machine we will show the 2 brushes. One will indicate the positive brush, the other one will indicate the negative brush, and the circular thing indicates the armature. So this is the representation of the armature of a DC machine. I will have the field somewhat like this. So I am showing the field in the form of an inductance because its primary function is to produce flux or magnetism. So I am going to show it as an inductance. So this is my field winding. Let me probably show this as F1, F2. This is the field winding. Let me show these 2 as terminals as A1 and A2, which are the armature terminals. So I am probably sending some current which is a variable current here. So this IF can be varied, and the variation in IF can be affected either by varying the voltage what I am connecting to the field winding, or I can connect the resistance in series with the field winding. Most of the times what we do is to connect the resistance in series in most of the cases, right? So I may have a resistance connected in series, and what I am doing is to measure the voltage here. So I am calling this as EG, that is the generated voltage. So at the given value of field current, I will be able to measure how much is the generated voltage, which will indirectly imply what is the value of flux that I have produced in the machine for this given field current. Of course, I have to drive this machine at some omega. If I don't have a prime mover, it is definitely not going to really generate any voltage. So I am showing this as the shaft which is being rotated at a speed omega. Right? So there has to be a prime mover. So the primary requisite for generator action is actually to have a prime mover which will impart mechanical power to the system, and I should also have the field excitation. If I have only residual magnetism, it is actually going to give very, very limited amount of voltage, nothing more than that, right? So with this, I am going to have this graph being followed by the machine. This is omega equal to omega rated. This is IF and this is the voltage EG. So we call this as open circuit characteristic. That is here. I may have a resistance connected in series if I want really a variation in the field current. Maybe I should show a very, very small voltage. It is not starting from the origin. I should have a small voltage. If there is residual flux, normally there will be residual flux. Unless I repeatedly excite the field in two opposite directions, which I won't do in a DC machine, normally. I will try to excite it only in one particular direction. If I am trying to excite it once in the positive direction, once in the opposite direction, then if I keep doing that repeatedly, I'm not going to have any residual flux left over. Not much, really. So I would basically try to do only one direction excitation. So generally the field coils will also be specified with where the plus should be connected and where the minus should be connected and so on. It will generally specify the terminal as well. When you generally purchase a DC machine, it will tell you in what direction the current should flow in the field coil, generally. Okay. So much so for open circuit characteristics. Whenever you do an experiment on DC machine, the first thing normally we do is to make the open circuit characteristics so that we know exactly what the back EMF constant is or what is the torque constant, so that you get a feel for what is the kind of rated torque it will generate if I pass rated armature current, right? Although everything is given in nameplate details, nevertheless, we would also like to verify the back EMF constant of a machine to start with so that you get a feel for the characteristic of the machine, right? Now, the field what I have shown it as though it is connected to a separate supply. But I can have different configurations of the DC machine depending upon how I am going to connect the field along with the armature. So let me try to look at the classification of the DC machine based on field connection. So I can have really a separately excited field. So the first one we are talking about is separately excited DC machine. When we say separately excited, very clearly I'm going to have a separate source for the field, and if it is a motor, I will have a separate source for the armature. Both of them will be completely independent of each other. So to show the connection, I should show it as though this is my field and I will apply VF here. Maybe I can have a variable resistance here if I want to vary the field. So this is F1, this is F2, right? And I'm going to have the armature. If it is a motor, I'm going to connect the DC supply voltage to the armature as well, which will be separate. So I will say VA, another voltage source, probably. If it is a generator, I will only connect probably a load here. So if I am talking about a generator, this will be the load. So I may have plus here and minus here, and the current will flow like this, right? Of course, if it is a generator, I should have a source for rotation. So mechanical power has to be input. So the field and armature are not directly electrically connected to each other in this particular case, and hence the name separately excited. They are not electrically connected at all. They are only magnetically coupled. They are not electrically connected, right? So it is like transformer action in one sense. They are not electrically connected at all, the rotor and the stator. Instead of having a separate excitation, I can also have permanent magnet, which means I don't have to give any electricity for the field circuit. I can simply have magnets, which are permanent magnets, like the normal magnets what we see naturally existing. So I will have the North Pole and South Pole, which are in the form of permanent magnet, but I can't vary this excitation. It is a given that the flux is going to be so much. I can't really vary the excitation. So here it's a constant excitation. I can't vary the flux. Whereas here it is variable flux. I will have variability in the flux. Right? Generally, permanent magnet DC machines, especially if we are talking about permanent magnet DC generator or even permanent magnet DC motor, they are all small scale toy kind of motors. Very, very rarely we use it for a real motor in an industry. We normally use it only for some kind of toys, or if we are talking about a generator, we use it probably in the case of, the tacho generator, where you may be sensing the EMF or speed. So if you want to sense the speed, we already said that the generated EMF is proportional to the speed. So let us say I have a rotating mechanism, right? Along with that, I have coupled a small generator, DC generator. So if I try to measure the voltage, what is generated, that will give me an index of what is the speed at which the shaft is rotating. So there I can have a permanent magnet. So whatever is the speed of rotation, correspondingly I will have a particular voltage generated. So this is generally known as tacho generator mechanism. So tacho generator is used generally for measuring the speed indirectly by looking at the voltage generated by the tacho generator itself, in which case it may be a permanent magnet. I would not like to have several connections in a tacho generator because it's a small one, it is a secondary mechanism. Why complicate matters? So generally I will have permanent magnet there. So this is one of the applications of permanent magnet generator. The second type of connection I may have is called shunt excited generator or shunt excited DC machine. Shunt excited means I'm going to have actually the DC armature is connected in parallel with the field, right? And I'm going to have probably the load connected here if I am talking about a generator. If I'm talking about a motor, I will have a common power supply supplying the field as well as armature. So I definitely need to have, a mechanism for rotating this if it is a generator. If it is a motor, I am going to have basically a DC armature here which is connected to the field in parallel, and together I am going to connect a V. Let me call this as terminal voltage rather than specifying this as field voltage or RMS voltage. Armature voltage. I am essentially looking at the whole thing as a terminal voltage. So this terminal voltage is going to supply both the field as well as armature. Right? Please note that if the armature is designed for 220 volts, the field will also be designed for 220 volts here. Which means the field winding is supposed to withstand a large voltage in this particular case. So it is generally rated for small current, large voltage, which means we are going to have high resistance in the field winding. So in this particular case, RF, if I may look at, this will be high because I am looking at VT divided by RF, which is equal to IF, is small. So the shunt field will be carrying normally very, very large number of turns with small amount of current. So large number of turns means I'm going to have thin wires made into huge number of turns which is going to make the MMF actually high because of the number of turns being high, not because of the current being high. Yes. Yes, that's what I'm saying. In this particular case, the first case, separately excited, they are electrically isolated. In this particular case, they will be electrically connected, but they are in parallel. But please understand that the field winding comes separately. The armature winding comes out with the brush connection. So external to the machine, I will connect them in shunt, not inside the machine. So generally the field terminals are brought out, the armature terminals are brought out through the brushes, then you connect them in parallel or in series or in whatever fashion you want, basically external to the machine, not internally. Internally they are never connected. So always the field terminals will be brought out, armature terminals will be brought out, and they will be connected external to the machine, normally. So if I want shunt configuration, I will connect them in parallel to the same voltage supply. That's it. So generally shunt winding is going to be characterized by NF being large and IF is small. This is how it will be. Right? So I am going to have NF, that is the number of field turns will be large, thin wire which will be wound over and over to make huge number of turns. And IF is going to be small, so NF times IF anyway, which is making up for the MMF of the DC machine, that will be pretty much large. The third type of connection, which is actually series. This is hardly ever used as a generator. Most of the times it is going to be used as a motor. Okay? Very, very rarely, hardly ever it is used as a generator. So I should say normally not used as a generator. Only as a motor it is used, but it is commonly used as a motor very, very often. In fact, all our cars contain a DC series motor for cranking up mechanism. IC engines have to be cranked up. They cannot start otherwise. The cranking up is normally done with the help of a DC series motor inside most of our cars, whether it is Maruti, Volkswagen or any of them, gasoline based cars, all of them generally use a DC series motor for cranking up. This is one of the major applications of DC series motor. So in the series machine, as the name indicates, I am going to have this as the armature. So let me again mention this as A1, A2, and I am going to have the field, which is actually F1, F2, and if it is a motor, I am going to connect a common DC supply here, which is being applied to both the field and armature together. And armature currents will be normally of the order of at least a few amperes or few tens of amperes, most of the times, because armature is the major power handling hub. So if I talk about 200 volts or 220 volts and the overall capacity of the machine is 2.2 kilowatt, then at least 10 amperes have to flow through the armature. So if 10 amperes of current is flowing, the same current would flow through the field as well. If I call this as IF and this as IA, I'm going to have IF equal to IA. So the current is going to be large. So series field current is large as against what we saw for the shunt machine. Shunt, we said the current is very small, whereas series the current is large. So I will have large ampere turns for this even by having smaller number of windings, smaller number of turns. So generally series field is characterized by thick coils which are just wound for fewer number of turns, which are carrying very large current. So we are going to have large current, and in this case NF, that is the number of turns, is going to be small. But thick conductors, because I am looking at this carrying a large amount of current. Right? Finally, there is something called compound machine, which will include both series and shunt. So compound machine includes series and shunt. The primary flux provider is shunt. Minor adjustments are made by the series. That's what is done. What I mean is, the shunt is going to provide primarily the flux that is required for the machine. But series, depending upon how much is the armature current carried by the machine, correspondingly, because if I don't have enough torque being developed in the machine or enough power developed in the machine, I don't have sufficient load, then there is no point in generating large amount of power. The voltage will be generated, but the current may depend upon what kind of load I have connected in a generator. Similarly, I may have the motor freely running. Depending upon how much of impediment I am putting on the shaft, I am going to rather look at how much is the torque developed by the motor. So for example, if I have an elevator, right? If only 2 of us get in, the torque developed will be very less. If 15 of us get in, the torque developed will be definitely more, because it has to go against the gravity for 15 people together. It has to lift all of us up, right? So the torque developed is going to depend upon what is the demand from the load side in the case of a motor. If the mechanical load demand increases, I'm going to have more and more current. If I'm going to have a generator, depending upon what kind of resistance or what kind of load I have connected, I'm going to have more or less demand of current, basically from the machine. So please understand this again and again. If I am talking about actually an armature, and if I am connecting a small resistance, I am going to demand more current for a given voltage. If I connect a smaller resistance, I am demanding more current. That means I am loading the machine more. If I am connecting a larger resistance, I am going to demand only a smaller current. So larger resistance means loading less. Smaller resistance means loading more in the case of a generator. Please understand this, right? It doesn't mean I increase the resistance, I increase the load. No. When I increase the resistance, I decrease the load. I decrease the power demanded. Because I'm always looking at a generator developing rated voltage. Never ever will you find a power station generating something like 300 or 350 volts. It is rated for 400 volts, 415 volts. It has to generate that. That is how it is. That is how it is adjusted. So it will always run at rated speed. It will always generate rated voltage, because I will always provide rated excitation. That's how it is, generally. Okay? So, if it is a compound machine, I am going to have series field and I am going to have shunt field. Both. So, I am showing both of them, and then they are connected like this. This is how it is. Right? So, let me call the shunt field as F1, F2. Maybe even here let me change this to FS1 and FS2 to show the series field. So let me write this as FS1 and FS2. This is the series field. And this is going to be the load. And this is of course A1 and A2. Please note, in this particular configuration, the shunt field is coming completely across A1 and A2 along with the series field as well. So we call this as a long shunt. It is coming across A1, A2 plus FS1, FS2. I can have instead a short shunt. I'll show you just by the difference. So I'm going to have the armature here. I can have the shunt just coming across like this, and then I'm going to have the series field beyond this. So this is generally known as short shunt, whereas this is known as long shunt. So long shunt comes across both armature and series field together, whereas short shunt comes across only the armature, nothing more than that. So I can put the series and then the load here. So please note that here my FS1 and FS2 have come here. This is my F1, F2. This is A1, A2, of course. Please note that the field is coming only across the armature here, not across the series field as well. Series field is going beyond parallel connection of the shunt and armature, right? So this is generally known as short shunt. We'll start off with first generator operation. Having seen the different configurations, we will look at the implication of these connections as and when we discuss the characteristics. When we load the machine, what happens? So we'll look at the implication as and when we look at the characteristics of the machine. So first of all, we'll start off with the separately excited generator. So I'm going to first discuss DC generators. And out of that, the first thing that we are going to discuss is separately excited DC generator. So most of the times in the laboratory as well as in many of the industries, if at all I am using a DC generator, which is very rare again, we are going to have invariably the same voltage supply available for armature as well as field. If I am using it as a motor, I might have the same voltage supply, maybe 220 volts or 400 volts. The DC value is fixed. Because of which, the separately excited field will also be in a position to withstand a larger voltage, normally. Whereas series, please note, it is having a voltage division between armature and the field. Whereas here there is no voltage division. I am having the entire voltage applied here. So I may apply maybe with the help of another resistance to adjust the current. I may have some VDC applied here. And that VDC may be whatever is the rated voltage in my factory or in my laboratory or whatever. So I will have here this resistance as a rheostat or the variable resistance that I am going to have. It's a variable resistance that I have. Right? So I can adjust the current definitely. So this is F1, F2 and the current is flowing in this direction and let me call that as IF. Right? And here is going to be my armature. I can initially plot the open circuit characteristics just by adjusting the rheostat value, or I need not even switch on the field to start with, and then I can just measure what is the voltage that is developed when I am rotating this at omega rated. I can measure how much is the voltage. Once I measure the voltage, I will get the residual EMF that is generated. So I'll be able to plot what is my OCC. So this is going to be my OCC by adjusting the field rheostat, right? And accordingly, I'm going to get different points in the OCC. When the rheostat almost becomes zero value, then whatever is the inherent resistance of the field circuit, that is going to limit the current, and hopefully that will be the rated current, because of which I'm going to get probably at rated value of speed, right? I'm going to get what is the rated voltage generated. So this is going to be IF rated. This is how IF changes. This is EG. So this is going to be E rated or V rated, whatever. Right. Now I am going to actually connect a load. Okay. So after I have checked up what is the value of back EMF constant and so on. I'm going to connect the load. So this is the load. Again, load probably is variable because I want to see when I draw more current, how is the terminal voltage? When I draw less current, how is the terminal voltage? Because it will be very similar to what I had as voltage regulation in the case of transformer. The transformer also we initially started assuming without any resistance and without any leakage. So we said E2 and V2 will be equal to each other if it is ideal transformer. But when I am talking about non-ideality in any machine, I am definitely going to have some inherent resistance for the armature. Although they are all copper conductors, thick conductors, no doubt, but I will still have some amount of resistance. So if I say that the field resistance is generally hundreds of ohms, armature resistance will be generally a few ohms or less. So it can be even milliohms, or it can be just 0.1 ohm, 0.2 ohms and so on and so forth, depending upon what kind of rating I am talking about. The larger the rating, the current carried will be larger, because of which the conductors will be thicker, so the resistance will fall. So larger the rating of the machine, RA will be smaller and smaller, right? Because the conductors will be thicker and thicker normally, right? So I'm going to have, these are some ballpark values, estimated values I'm telling you. I'm not asking you to memorize these things. These should become your second nature. Eventually, when you read so many problems, read through so many problems in the DC machine, invariably you will see that the field resistance will be given as 50 ohms, 100 ohms, 150 ohms, whatever. Whereas armature resistance will be given as 1 ohm, 0.8, 0.01 and so on and so forth. That's what you would see. So the armature resistance is generally very small. But when a current is flowing in the DC machine, although 220 volts were probably generated originally when it was under no load condition, I'm definitely going to have a drop which will correspond to IA-RA. If IA is, let's say, 10 amperes, and let's say I'm going to have my armature resistance as 0.5 ohm, then 10 multiplied by 0.5, I will still have 5 volts drop. So from 220, I will have a drop of 5 volts. So the terminal voltage, if I try to measure now, this may be only 215 volts. So this I would call as VT or VL, the terminal voltage VT. VT will keep falling further and further as I increase or as I draw more and more current from the generator. So if I try to plot how VT is as compared to what my armature current is, please remember or notice that you are going to have IA and IF independent of each other because they are supplied from two different, entities. So I have generated voltage which is supplying the load, which is also the armature current, and I'm going to have actually whatever is the field current that is decided by what is the field resistance and what is the field supply. So the two are independent of each other. So I am going to have this as IA, this as VT. When my IA is 0, I had this value to be EG at rated speed. Of course, I am talking about rated condition of speed, rated excitation. When I provided rated excitation and rated speed, I had EG as my value of generated voltage. Now, if it had been an ideal generator, this should have been maintained as a constant. But it is not ideal, clearly. So, I am going to have definitely a fall in the voltage. But the fall in the voltage is not much normally in a separately excited machine because the armature resistance happens to be generally very, very small. So I will have generally the drop in the voltage, IARA drop, as compared to what is EG, the original generated voltage, it will be less than 5 to 7%. It will not be definitely more than about 7-8%. So this is really, really small. So this is, actually if I say this is the rated current, so this is IA rated. I'm going to have this drop, what I am getting as IARA drop. So I'm going to have IA rated multiplied by RA is going to be less than, most of the times, about 7 to 8% of EG rated. So RA is generally really, really small. That's what I'm trying to emphasize, right? So I should be able to write some of the equations, electrical equations, based on whatever characteristics I have drawn. I can say VT is equal to EG minus IARA, right? And I should be able to write also that IF is equal to VDC divided by RF plus maybe R external, if I may call this as R external. What I have connected as the external resistance, I am calling that as R external. Right? And I should be able to say EG is also equal to some constant which corresponds to the number of conductors, number of poles, all those things multiplied by IF, because IF decides what is the flux, multiplied by omega, at which I am driving the machine. Right? So, in this particular case, there is no correlation between IF and IA. RF is the field resistance. RF is the field resistance, inherent field resistance, which will be of the order of 150, 100 ohms, 150 ohms or whatever. So this is field resistance. So these are the equations which govern the operation of a separately excited DC generator. K is actually the constant. I cannot write this as KE because KE when we write phi multiplied by omega. KE multiplied by phi multiplied by omega is EG. But now I am not writing phi, I am writing IF because IF is an electrical quantity. Whereas phi I have to bring in magnetic circuits. So that's why the K still corresponds to the back EMF, but back EMF constant, but if actually I eliminate phi and instead I put IF, then the proportionality will change, right? There will be reluctance, inclusion, number of turns and so on and so forth. So the K is still related to the machine constants, which are like parallel paths, number of conductors and so on and so forth, poles, all those things, definitely. Okay? So this is going to be these are going to be the equations that govern the operation of a separately excited DC generator. By the way, because this, whatever we observe here is the load terminal voltage and the load current, it is external to the machine. So we call this as external characteristics of the machine. External characteristics of the machine. Whereas this is open circuit characteristics of the machine. Now a small twist I have to introduce in the external characteristics. All along we are assuming that the flux is unaffected by any armature current that is drawn. But the armature current is not going to keep quiet. it will also establish its own flux. Because it introduces its own flux, the main flux which was created by the field will get modified, whether I like it or not. As long as the armature was open circuited, it was just developing the voltage, the main flux was just, hale and healthy. There was no problem. But the moment I connect the load, the armature is going to start carrying current. If the armature carries current, it is definitely going to throw its own spanner into the entire field of things. So I am going to have some variation in the flux in the form of something called armature reaction. So we'll have to look at what is the reaction of the overall flux to the armature flux. That is known as armature reaction. The net effect of armature reaction would be to reduce the flux to a certain extent. But there may be some saturation involved, there may be some other crossover involved, because of which it is not a linear reduction as compared to the armature current being increased. If armature current is 5 ampere, if the flux is getting decreased by 0.2 Weber, it doesn't mean if the armature current is 10 amperes, I'm going to have reduction by 0.4 Weber. No. So, I will have actually, if I try to look at it, the drop will not be linear, it is going to be non-linear as far as the armature reaction drop is concerned. We are going to discuss armature reaction in a little greater detail. But I am just trying to say that it is not linear. It is non-linear, because of which I am going to have, I would rather say, this is armature reaction drop. This is called armature reaction drop. So the armature reaction drop occurs in a DC machine in addition to IaRa drop. IaRa drop is because of the physical resistance of the DC motor's winding, armature winding. Whereas the armature reaction drop is essentially due to the armature flux interacting with the field flux and maybe bringing down the overall value by some quantity. So that is going to cause a reduction in the overall voltage that I am visualizing at the terminal of the DC machine. And this will definitely increase as the armature current increases, because the reaction will increase, definitely. But it is not a linear increase. That is a little non-linear, and that's why I'm not showing this as linear, it may be non-linear. Right? Now, originally if I had considered where the operating point for a given load resistance is, this is RL. Let me show this as RL. So I have to draw basically the load line. If I am looking at the load line, this is the load line. Load line is IL multiplied by RL or IA multiplied by RL. What is the voltage correspondingly? Where these two intersect, this would have been the operating point originally. But now, because of the armature reaction, they are intersecting somewhere else. So I am definitely going to have a little different value of the operating point, that is the voltage as well as current, both are going to be somewhat different as compared to what actually I visualized originally as the operating point. This was the original operating point, this will be the new operating point as per the armature reaction effect is also included. So we will look at what is armature reaction in the next class.